Oh my goodness. Anyway, this is important. Not erase it. But anyway, we'll follow up from this itself. I'll redraw it again. Uh, questions. Otherwise, we sort of begin where we left off yesterday. E, the most general scheme is E plus S is ES going to E plus P. This could well be a reversible reaction, and then E plus I going to EI. And this may well combine with S again to form EIS, and ES may well combine with S. Sorry, let me say. May well combine with I. May well combine with I to form EIS, and this may also give EI plus P. And we sort of put something like the Km here, and then Ki here, then Km here, or Ks if you want to. We use Km for non-reversible reactions, and Ks is being used for reversible reactions, right? And Ki and this we wrote as Akm, or what Km by, I don't remember. I mean, it's hardly matters, 1 upon A or A, right? And so this is AKI. I mean, if it is A here, then it's A here. That is what we proved yesterday. And we also said that this could be some K2, and if this is K3, this can be written as B into K3. Now B can be put here, and if B is 0, then of course this is a dead-end complex, and if B is 1, then this is as fast as the other reaction, and if B is more than 1, then obviously there is an activation going on. It is no longer an inhibitor. So that makes sense, right? And we sort of essentially derived the fractional saturations. What was the fractional saturation in terms of ES? ES upon the first fractional saturation is E plus, that is ET, which is E plus ES plus EI plus EIS. And if this reaction is indeed active, as we were discussing, then, and this into K2, or rather this is the fractional saturation, this into Vmax, right, would be the rate of reaction, where Vmax is nothing but K2 into ET. So this is the ES, so we can put Vmax here. Does that make sense? Right, because the actual reaction is K2 into ES, and so, and K2 into ET is Vmax. So if we know the fraction, then Vmax into this fraction is nothing but the rate of reaction. And similarly, we could have the equivalent of Vmax here and have the fractional saturation, this part here, the fraction, the Vmax is multiplied by both, so it would be EIS upon the same in the denominator, E plus ES plus EI plus EIS. Make sense? Is that all right? And of course, this would be multiplied by that B factor if we had this as B. So what is the rate of reaction?
Sir, how this EIS upon E plus ES plus EI upon EIS, this part came?
Just like this one. Suppose that this reaction was active. We were assuming that this reaction was active, right? We were assuming that this reaction is active, and therefore this is a dead-end complex. We were assuming that this is a dead-end complex. This reaction is not taking place. So assume dead-end. In which case, if this is a dead-end, then as far as we are concerned, we are simply interested in the fraction of ES upon ET. The fractional saturation is ES upon ET. Right?
Yes,
ES upon ET.
Yes, sir.
Right, and this into Vmax is the rate of reaction, because the maximum rate of reaction is given by this expression here. Correct? And the actual rate of reaction is K2 into ES. Okay? But I could well have a reaction rate V is equal to K2 into ES Okay, plus K3 into EIS. If K3 is not 0, if this assumption is not valid, this is a question. So I should put K3 into EIS, and later on I can simply put K3 equal to 0 if indeed this is a dead end complex. That's the most generalized formulation that I can think of. Okay?
Yes,
And
yes.
K3 I am writing it as, I mean, just for convenience, K3 I am writing as equal to VK2. In which case it is K2 into ES plus V into EIS. Okay, and ES in terms, now we have to simply write ES in terms of ET. ES in terms of ET, which is this expression here, the fractional saturation. So we can replace it. This is equal to fractional saturation. Notice that this expression obviously is ET, obviously. Right, so ES upon ET we know, so we know that ES can be written in terms of ET. That is all. Simple enough. This is also ET. So, I mean, I hope you have understood this simple algebraic strategy that we are following here. So I'm just sort of re-emphasizing the point that this is the total amount of enzyme distributed between free enzyme, bound, different types of bonding, free enzyme, bound. So there are 4 forms in the enzyme. The 4 forms are this one, and this one. So this is the total sum of total enzyme. But since in the reaction mix you are going to add ET, you don't know how it is distributed. So you will sort of say that the maximum reaction is when everything is ES. All the ET is essentially equal to ES. So V max represents is nothing but K2 into ET. That is why V max increases as ET increases. Right? But the real V is actually K2 into ES. Or actually, as I'm saying, it is actually equal to K2 into ES plus K3 into EIS, if the most general equation is valid, which is equal to K2 into ES plus B into EIS. Okay? All of you have agreed with this? Sort of re-emphasizing the obvious, but still, because I can't see you, I cannot make out. So that is why one has to go slow in online classes. All of you are okay with this?
Yes, sir. Yes, sir.
Yes, sir.
Yeah. Okay. So now, given this, and now I will rub this part out. So you know what it is, you know. So we will not assume any dead end. And so now tell me, now please sit down and derive that expression, the complete expression for V. Please use your pen and paper and derive for me. My algebra is very weak. So let us now do this. Please let us do V is equal to, and what did we do? We derived it in the last class.
VM ES upon E.
So VM and
ES
ES is
upon
what?
ES
E into S. E
upon
into
KM.
S. E into S upon Km. And this is
E plus
E.
E into S upon Km plus E into I upon Ki plus E I into S upon K2.
I plus E into I into S, right? Correct?
Yes, sir.
E into I into S or E upon Km Ki. Is this okay? No. गलत हो गया. A तो गायब हो गया आपका. A आएगा यहाँ पे एक. People have forgotten the last class. You have to go back and study a little bit. And so when I divide by E, and then I can simply get this as, right? This was for ES. And what about ES, EIS? So we'll have to write plus Vmax, and I have to get the B term here, right? And what about the EIS? The EIS is E into I into S upon A Km Ki. Okay, and maybe I'm doing it wrong. I've divided by the same fraction, E plus E by S by Km plus E into I upon Ki plus E into I into S by A Km Ki. Or it is 1 upon A, I do not know. I mean, this algebra I wanted to go back and do. And so we divide by E gone. So we have this term here, the second term. Okay, and so let us do some amount of rearrangement and a little bit of algebra. And so all of you are okay with this, right? I might have made a couple of mistakes, usual with me. I can't divide and multiply correctly, so I might have made a couple of mistakes here and there. But you have to go back and sort this out with a paper and pen. I'm doing it right on the board, listening to you, and also trying to get the thing right. So therefore, V was nothing but, as I said, Vmax. Sorry, key spelling. So I would write it as Vmax, right? S upon Km. I mean, I could write it upon Km, or I could multiply everything by Km. I could multiply everything by Km here and get down, and this would have been 1 earlier. So I would get it as Km. Come on, let us have some opinion from you guys. Km plus S plus
I Km I upon Ki.
Km I upon Ki
Plus I upon
notice. Yeah, plus
I upon AKI.
I upon AKI.
So I into S. Right?
S, हाँ, S तो भूल ही गए आप भाई, आप बहुत गलत मुझे वो गाइड कर रहे हैं.
सर ये तो S
ठीक है, ये हो गया ना.
So A क्या
ठीक है, एक ही आई, सॉरी, एक ऑफ कोर्स ए
सर AKI.
Yeah, and this is for the E into S plus, you know, if I had the second expression also there, then Vm here, Vm S B by AKI. ठीक है ना, ये वाला Km से डिवाइड कर दिया था इधर, है ना, तो AKI नीचे रह गया. Are you okay with this? Am I doing it right?
Yes, sir.
ये expression normally मैं मतलब I am considering the EIS complex also. This is the EIS complex, and so we get now a simple expression which is Vm what? Vm S बाहर ले लेते हैं as usual. 1 plus क्या होगा? B by AKI ना? Is this okay? Just tell me if it's okay. And then I take Km common here, and so I get
1 plus S by Km.
नहीं, 1 by I by Ki. क्या कर रहे हो आप? प्लस S, ऐसे चलो ना, 1 plus I by AKI, right? Make sense? I took this and this and this and this. So fine. Now this is now easy enough. Now you can make out, and I will rub this above part out again now because I can't make it smaller. This part off. So this you notice that, and now you can see how it is going. For example, the simplest case that we did in the class was about competitive inhibition, which is E plus S, ES going to E plus P is monod kinetics. This we have already solved. E plus I, EI, backward, sorry, EI And this is competitive inhibition. I and S compete for the active site on E. So they compete with each other. Nothing else is there. There is no EIS term here, so this part is gone. So this part is gone. And there is no I by Ki. This stuff is gone. There is no A here. That's okay. And there is no. Okay. This part is gone. So we come to, and this part is gone. So how does this solve here? This solves here as V is equal to, notice, it stops here. There's no here, this term is gone, and obviously this term is gone. So it stops here, and it says Vm S upon Km plus S plus Km I by Ki. Right? That is where it stops. And this is competitive inhibition. So now we are deriving the specific cases from this generalized model. Spelling ठीक है competitive का inhibition. ठीक है? Okay. So competitive inhibition is when the inhibitor and the substrate compete for E, and the inhibitor leads to a dead end complex. Nothing goes here, and otherwise the enzyme interacts with substrate, forms ES, goes to E plus B. And so this is what it is. And therefore, as you can very obviously see, this is nothing but VMS upon Km 1 plus I by Ki into plus S, which of course, if Ki was not there or I was not there, would reduce to the monod kinetics, which is VMS upon Km plus S. The simplest of the cases where even this was not there. Even this was not there. E plus S, ES. So obviously it will reduce to that. So now this was added. So now let us, from the generalized model, let us go back and remove other stuff. All this other stuff you remove. All these things you remove. So only this part is there. So complete inhibition represents nothing but this equation, which is also this equation. Is this all right? And so what does it show us? Can I rub this out? Will you remember this part? We will come back to this. So what do we see here? We see here a rather simple situation of competitive inhibition where the Km is changing. So there is a Km, there is a Km, this Km is now some Km apparent, which increases as I increases, or if Ki is small. Which means that this binding efficiency is very strong, or if I is strong, then Km will change. That makes sense, doesn't it? See, if I had a huge amount of substrate, very large amount of substrate, doesn't matter how much inhibitor I had. Doesn't matter how much substrate inhibitor I had. If I had excessive substrate, everything will be favored by this reaction. The enzyme will be saturated by substrate. So I would therefore have also the maximum V is equal to Vmax. So the Vmax value, notice when S is very large, this is very large, this is very large, S is much larger than Km, it is also much larger than Kmap, and therefore S and S can be cancelled out, and therefore the V is approximately equal to Vmax. V is approximately equal to Vmax. So Vmax does not change, Km changes. So no inhibitor, the usual reaction V is equal to V versus S. This expression here. And as we keep on adding inhibitor, the substrate concentration, and you can see that as inhibitor increases, this is the point, right? This is what we call as the the geometric interpretation of Km, which is half the maximum velocity. So you can see that the Km is increasing as the inhibitor is increasing. So this is Km apparent, which of course, as your inducer, as I increases, you will have higher and higher values of Km, and hence, so notice that the velocity will go to the maximum at a much slower rate and will require a much higher concentration of substrate. And at lower substrate concentrations, at any low substrate concentration, where you could have had this velocity with increasing inducer concentrations, velocities are lower at any given substrate concentration. Makes sense, doesn't it? Because I is now competing out the enzyme. And so at low substrate concentrations, I beats E and I captures E much more efficiently at low substrate concentrations. So therefore, your reaction rates declines. But at very, very high substrate concentrations, this decline is negligible because substrate saturates it, I is not able to compete it out. So high substrate concentration, so Vmax is a constant, theoretical Vmax, but Km apparent is a function of I. And so you're effectively the ability of substrate, the enzyme to pick up substrate efficiently, which is the measure of Km. Km is after all nothing but not just the half of Vmax, the substrate concentration half of Vmax, it's also the affinity of substrate towards enzyme. You know that, right? Hello? Do you know this point that Km represents the affinity for the substrate?
Yes, sir.
Yes.
Obviously, because it really represents how much you can retain a high velocity even at low substrate concentrations. So a typical graph of like this represents the fact that as you lower substrate concentrations down, you do not get a lowering of velocity till the substrate concentration becomes really, really low. So it's a very efficient enzyme, is a very efficient scavenger of substrate. But the increase in Km represents nothing but the fact that it's no longer efficiently able to scavenge substrate because it is trapped by the inducer. And the more it is trapped by the inducer, the more substrate you will require to replace the inducer in a competitive fashion and become ES, which is actually giving the product. So it all makes a very reasonable sense. Okay.
Sir, Km apparent is not the Km apparent is not the actual Km of the enzyme.
Well, this is what you will observe. There is no such thing as the only actual Km is this Km. This is the Km of the enzyme. And the Km apparent is this whole expression. Because you tend to plot it like this. Because when you will plot, how do you plot it? You plot 1 by V versus 1 by S. Of course, you don't plot 1 by V versus I have told you in the lab practicals that you should not plot 1 by V versus S. Now, what is 1 by V versus S in this equation? V इसका reverse करिए क्या होता है 1 by V is equal to Km. भाई बताइए क्या होता है Km by Vm
plus Km by Vm
1 by S plus 1 by Vm
plus 1 by Vm.
ठीक है ना? This is the equation, right? So the intercept is 1 by Vmax, so, but the slope
Yes.
is Km by Vm. So really, what you will get as the data will be like this. They will all intersect at this point, at the y-axis, because this y-axis intercept is nothing but 1 by Vmax, and that is not changing. The y-axis intercept means x is equal to 0. That means substrate is equal to infinity. So at infinite substrate, the velocity will be equal to Vmax. That cannot change. This is the Vmax at I. But as you lower the substrate concentrations, your velocity does not increase proportionally. So as you can see that the velocity, this is different I values. Now please tell me whether this is increasing I or this is increasing I. This much at least you should be able to tell me. So notice this direction, substrate going down, substrate is falling, and this direction, velocity is falling. So please tell me, if I plot 1 by V versus 1 by S, the slope is Km by Vmax, right? And Km is increasing with increasing inhibitor concentration. This is Km apparent, isn't it? Because what you're plotting is this, so you are using Km apparent. So obviously, this side is I increasing. The slope increases as you increase the inhibitor concentration. And this is what you were supposed to have plotted in the practicals. So I thought you would remember this. Does that make sense? 1 by Vmax, the intercept, the y-intercept does not change, but the slope of the function of the double reciprocal plot or the Lineweaver-Burke plot the double reciprocal plot is actually going to change. It is going to increase as Km by Vm. So you can find out the slope values at different inhibitor concentrations, find out the Vmax from the intercept, and then find out the apparent Km for every different inhibitor concentration. Substitute it in this equation here, Km plus is equal to Km apparent, to find out at different inhibitor concentrations, your inhibitor concentration is changing, and from there you can simply find out the value of Ki. Right? This algebra I will not do. Is it obvious?
Yes, sir.
Yes, sir.
This is obvious algebra. So now I will expect you to solve. This is the kind of problem that you have already done in your lab practicals. I do not know how you submitted lab practical notebooks without having understood this basic point. So I will not do the actual problem solving exercises. They are there already in your lab practicals. Please revisit them and plot 1 by V versus 1 by S for different inhibitor concentrations. Find out Vmax, Km apparent. From there, at different values of I, find out Ki. This is a job, right? So this is a assignment which is not a graded assignment. It is to help you get a feel of the numbers involved. So what happens when, so the reaction rates tend to sort of increase more and more slowly with substrate if your substrate concentration, if your inhibitor concentrations are high or your Ki values are high. So notice that this is a simple derivation from the more generalized model. Is this all right? Clear? Now, let us consider the next case. So this is called competitive inhibition. Competitive inhibition is this model. And this, oh no, before I stop, I would like you to now remember the Haynes plot and the Eadie-Hofstee plot, and I'm sure you have forgotten. कितने लोगों को याद है? अगर याद है तो I would be very impressed. Eadie-Hofstee plot. They are different.
I remember one is S by V versus S and one is V by S versus V. I don't remember.
Absolutely fantastic. I am absolutely S by V versus S. And so you tell me in competitive inhibition, like in this plot, the double reciprocal plot, what happens is here is this one. This one, I'm sorry, I'm making a mess of the whiteboard, blackboard actually, whatever. Then this kind of plot, how would the fact that Km apparent is changing with different inducer concentrations, how would the plots look like at different inducer concentrations? And how would you determine the value of Ki, real Km, not the apparent Km, and the Vmax? Haynes plot and Eadie-Hofstee plot, how would they look like for competitive inhibition with different amounts of inhibitor added? And how well then will you really the idea is very simple. Determine parameters, parameter determination. Vm and Km, this is Km two places here, and Ki. By adding different amounts of substrate and inhibitor and measuring velocity, you can determine the parameters of the model Vmax, Km, and Ki. Okay, that is all that is there. So it's exactly similar to any modeling technique where parameters are estimated from experimental data of different S values, different I values. You find out velocities, and from this data you make such plots. And you find out Vm, Km, and Ki. The problem becomes complicated because there is error estimation, which I have not yet taught you. One of these days, I will go down to and teach you error estimation also, because that is also an important component. Or maybe I will use one of the lab practicals to do it because we don't have time. How do you estimate these numbers and how do you estimate their confidence limits, given that there are errors in the measurement of S, I, and V? And so why and when is least square not a good idea, and when is it a good idea? Now let us sort of rub out everything. Okay, let us rub out everything. You will remember all this. So really now we come to the other part, which is what we were talking about, which is, let us say that we'll take each we had now this E plus I here, and no, let us forget this part, and let us say E plus S, sorry, E plus S is ES going to E plus P, and let us say that ES binds with I, forming the EIS. And again, let us assume that this is a dead-end complex. Now what is happening here? The I binds with E even as the substrate binds with E. So they are not competing. They are both binding to E. There is no So obviously, most probably the sites are different. So earlier, in the competitive inhibition, the substrate molecule and the inhibitor were binding at the same point. That is why there was competition. That was this competitive inhibitor. If this bound, this could not bind. If this bound, this could not bind. But now we have a different situation where the inhibitor is now binding at this point. So this is the EIS complex here. And if this binds here, then this no longer can make product. This is not possible. So some of the ES quickly goes to E plus P and releases enzyme, but some of the ES gets bound to I, depending on, of course, the concentration of I and the binding constants, etc., and therefore forms a dead end complex. So this is not competition here, so it is called uncompetitive inhibition. So that was competitive inhibition, this is uncompetitive inhibition. Again, a component of the mixed larger model where now these pathways are gone. These three pathways are no longer there. These are off. Earlier, everything was off. This was on, competitive inhibition. Now you have uncompetitive inhibition where this pathway is on and everything else is off. Is it clear?
Yes, sir.
Yes. Yeah. तो अब बताइए भाई इसका क्या formulation होगा? So now tell me, for the simple case, V is equal to
Vmax
E into S
upon Km.
सही बात है.
Upon
and then E
plus E into S upon Km plus E into I into S upon
हाँ भाई AKI हाँ AKI KM ठीक है
yes sir AKI KM
ठीक है okay so now again let us simplify 1 ठीक है ना so this becomes equal to and then Vmax S multiplied by Km and we write Vmax S Km से मल्टीप्लाई कर दिया तो नीचे हो गया ये Km प्लस S प्लस IS upon AKI huh? Okay so this is uncompetitive inhibition. So this is the advantage of fractional saturation logic. You see, if I were using Briggs-Haldane and doing a steady state approximation, I would be in a lot of trouble. I would have, my equations would have been much more irritating. Is this all right with all of you?
Yes, sir.
Okay, so now therefore, I mean, I'm not, waste time on the algebra. I rather waste time on the concepts. You people are supposed to be damn good at algebra. I mean, never been able to solve any of the JEE questions. They're so difficult. So I'm sure that some of it you have retained over time. So what is this? This is Vmax. V is equal to Vmax. Come on, let us have it. S upon Km plus S into 1 plus I by AKI, right? Right? Is this all right? So let us work this out. So you can see that this is what is happening in the uncompetitive inhibition. So now tell me, now Km is, it's not Km apparent, right? It's a problematic situation because now to write it in the form, V is equal to some Vmax S upon Km. We want to write it in the usual monod form. If you want to write this, it is not easy to write because we can take this as some, what do you call it? Alpha, let us say alpha or beta or whatever. So then we will have to write this as Vmax and then we have to divide it by alpha, numerator and denominator. We'll have to write Vmax upon alpha S upon Km by alpha plus S. right? Is this all right? And so we have both Vm apparent equal to, hello, can
Yes,
all of
sir.
you hear me? Yeah.
Yes, sir. Yes, sir.
So we have
Yes, sir.
both Vmax apparent. है ना? We have now divided it by 1 plus alpha. And so we have both Vmax apparent is equal to Vm upon alpha, which is 1 plus I by Ki. Right? Notice that Vm is becoming smaller because the moment I increase I, this number, if I is 0, then Vm apparent is equal to Vmax, and Vm is becoming smaller. Right? But Km is also becoming smaller. Is it not interesting? But Km is also becoming smaller. Notice. It's becoming Km upon 1 plus. But even though Km is becoming smaller, Vm is also becoming smaller. So while Vm has a direct first order, direct proportionality with velocity. Right? It's direct proportional. So the real effective rates actually tend to decline, as is obvious from this equation. So 1 plus I by K. So both Vm and Km are declining. So now let me ask a very simple question. How do the plots look like in uncompetitive animation? If, let us say, let me ask the simplest one. What is the 1 by V versus 1 by S look like? So now notice that the 1 by V, what is the equation? 1 by V is equal to, I do not actually, is equal to Km by Vm into 1 by S plus 1 by Vm. Right? So both slope and intercept are changing. The slope, sorry, and what am I saying? The intercept is changing because this is now Vm apparent. Intercept is changing, it is becoming smaller, but Km upon Vm, notice, or Vm upon Km is exactly the same because both are divided by alpha. Right? So the slope Km by Vm, because Vm by Km, the slope is unchanged. So really, the graphs that I will get of 1 by V versus 1 by S for the case of uncompetitive innovation will be like this. Notice that the graphs that we got for competitive innovation were like this. They were slope different, intercept same. Here intercept is different, slopes are the same. And obviously, as you can see, that these points represents Vmax and Vmax is declining. So 1 by Vmax is increasing. So as we increase the inhibitor concentration, the slopes tend to shift upwards. The lines tend to shift upwards in parallel. So for 1 by V versus 1 by S plot for an uncompetitive inhibition is going to give you parallel lines with different intercepts, and the different intercepts all represent 1 upon Vmax apparent, from where you can find out the 1 plus I by Ki if you know how much the slope has changed with different I values. And so you can find out Ki and you can find out Km and Vmax. Is this argument clear?
Yes, sir.
Yes, sir.
Okay, so now, so this is competitive and uncompetitive innovation. And there is another term that I thought I should cover. We have time? Yeah, we have a lot of time. I'm going reasonably fast now. So is this clear? So competitive and uncompetitive innovation, the mechanism, the difference in mechanism, and hence the difference in equations, and hence the difference in the plots. So depending on whether the inhibitor is competitive or uncompetitive, you will get different plots and you will get different charts, and you have a different concept involved here. I binding at the same site, or I, that is competitive, I binding at a different site and again generating a non. And remember, we are not talking of EIS being active. If EIS were active, then we will come to that later. So now, when both things happen, then it is called a mixed inhibition kinetics. So when you have both ES, E plus S, going to ES, going to E plus P, obviously, and this plus I is EI, which is a dead-end complex, and ES plus I is a EIS, is a dead-end complex. If both things happen, then, and notice that if I can bind with EIS, theoretically this one is also active, right? This is EIS. Because I mean, if the enzyme is binding here and the substrate is binding here, or the inhibitor and substrate are binding here and here, whether this one binds first and forms an EI and then S adds, or first ES binds and then I adds and becomes EIS, it really does not matter. Right? This comes first or this comes first. So whether you get an EI complex earlier or you get an ES complex earlier, it doesn't really matter. As long as we are concerned, the enzyme binds with I and with S and reaches EIS. It could happen like this and it could happen like this, right? Both ways it's the same thing. So both things happen. Of course, I'm not taking this as this. I am still assuming to be a dead end. Let us assume for the timing. Now, this kind of inhibition, where both inhibition systems are active, is called mixed inhibition. And so now the equations would be, बताइए.
V is equal to V max.
These are all simplifications of the last equation that I wrote, right? So it really should not be too difficult. So ES is V max, and then ES is E dot S
upon Km.
And then is E plus E into S
upon Km
plus
E into I upon Ki plus E into I into S upon K Ki Km.
I'm sorry, yeah. ये अब फाइनली हैंग करना शुरू हुआ. आई थिंक इट टेक्स वार्मिंग अप करता है फिर हैंग करना शुरू करता है. ये बहुत बड़ा ट्रबल देगा. EI is upon AKI or AKI KM, right? Right?
Yes, sir.
Okay, so we have therefore a situation where this is the basic model, and then can you simplify this? Again, divide by E. And so we get this equal to as Vmax S upon this thing at the bottom. Let us say this thing at the bottom. I mean, I'm not going to write it again and again. So this is mixed inhibition. Now, a very special case of mixed inhibition is when A is equal to 1. A special case of mixed inhibition is when A is equal to, special case is when A is equal to 1. Which means that this, remember this was AKI, this was KI, this was AKI. Right? Which really means that the inhibitor binding to the enzyme and the inhibitor binding to the enzyme substrate complex are exactly equal. You understand? So whether the enzyme is like this and the inhibitor comes and binds here is independent of whether the substrate is bound here or not. This efficiency of binding is not impacted upon by the presence or absence of substrate in the active site. Does that make sense? Think about it. If A is equal to 1, what is it that I am saying in real terms? I am simply saying that this binding, the binding of I with ES, is the same as the binding of I with E. Which means really that if substrate is present, then it has a certain binding affinity with respect to enzyme. And if substrate is absent, there is a certain binding affinity. These affinities are exactly equal. So the enzyme substrate complex binds with the inhibitor in the same efficacy as the enzyme free enzyme which has no substrate. In which case I is equal to A is equal to 1. Is that okay? And such things are called, this is called, see, competitive, this is called non-competitive. And a lot of people get confused about non-competitive and uncompetitive. So this is called non-competitive inhibition. So competitive inhibition, uncompetitive inhibition, and this is called non-competitive inhibition. So some inhibitors behave in a non-competitive manner, which is essentially mixed inhibition, but with A equal to 1. So they are able to bind with the EI complex in a way and it combines and it attacks every point. So now in which case, what do we have here? What is the mixed inhibition non-competitive model here? So Vm upon, let us have AI gone here. So what do we get? And multiply by Km. So we get E ko kaata aapne. So Km plus S plus, hello?
Sir,
Are
S
you
upon
there?
Km plus I upon
Yes, sir.
Ki.
Plus Km I upon Ki plus S I upon Ki.
Ki.
ठीक है? Okay?
Yes, sir.
Okay. Which really, interestingly, notice is now making us what? Which really means that this term here, this expression here, means V is equal to V max S upon Km 1 plus I by Ki plus S I 1 plus I by Ki. Isn't it? Okay? Hello?
Sir,
Right?
this is non-competitive inhibition.
This is non-competitive inhibition. Which, if you simplify a little bit more, can you tell me something? A very simple and obvious simplification? Multiply numerator and denominator.
Sir,
1 plus I
sir,
by Ki.
VMS upon Km plus S into 1 plus I by Ki.
Vm
S.
Into 1 by 1 plus
divided,
I by
divided,
Ki.
divided.
Yeah, sir.
1 plus I by Ki upon Km plus S.
So really, Vm apparent is equal to Vm upon 1 plus I by Ki. So notice that only Vm apparent changes. When you have non-competitive inhibition, there is no change in Km. So earlier we had a change in Km only. Second, we had a change in Vm and Km, but they were proportional. And now with non-competitive inhibition, there is a nice symmetry about it. Only Vm changes. Vm falls, but Km does not change. Km remains the same. Got it? So only the Vmax is changing. The Vmax is nothing but this number here. This is the Vmax apparent. Right?
So
Let me
what's
sort
the
of pause here. Wait.
difference
Yeah,
between
I think we
the
have run out of time.
non-competitive?
Sorry, yeah, go ahead.
So what exactly is the difference between the non-competitive and uncompetitive inhibitions?
Oh,
Like biologically.
huge difference. No, don't turn in terms. Non-competitive is mixed inhibition kinetics. Uncompetitive is when this enzyme binds only with the enzyme binds only, sorry, the inhibitor binds only to the enzyme substrate complex. In the, sorry, I should have drawn it better. Actually, I made a mistake. In the non-competitive case, let me sort of draw it. In the non-competitive case, it is also equally important that this this is the enzyme and this is the substrate and this is the inhibitor. It binds here, it binds here. I should have drawn it properly. I made a mistake. So this is non-competitive. Non-competitive is where it binds and competes with the substrate for the active site. It also binds independently. So it binds with E, free enzyme, and makes I. So it actually is a mixed inhibition kinetics, which means it binds with the EIS complex, which is this and this. These two are, this is when this is the EIS complex, and this is the I complex. Just directly, when enzyme is not there, sorry, when the substrate is not there, when it is absent, it will go and bind to this. So it competes with the substrate for the active site. But when it is not competing, it also goes and binds to in an uncompetitive fashion. So it non-competitive is actually not uncompetitive. Non-competitive is actually, you realize, non-competitive is actually a misnomer. Non-competitive is a mix of competitive plus uncompetitive. Non-competitive is competitive plus uncompetitive. So non-competitive represents both a mix of competitive and uncompetitive, and therefore non-competitive is actually an example of mixed inhibition kinetics. It is not, see, competitive and uncompetitive were not mixed inhibition. It was either E plus I EI, or it is either ES plus I is equal to EIS. But now you have mixed inhibition where both kinds of inhibitions are working, and non-competitive is actually a special case of mixed inhibition where the competitive and uncompetitive parts are exactly equal. A is equal to 1. So non-competitive is quite different in terms of principle. It looks very similar, but it is actually the most different from the other two. Okay. So non-competitive is actually mixed inhibition kinetics and nothing to do with uncompetitive or with competitive. It is a combination of both. Is this clear?
Yes.
So let us stop here. I think I know this is simple algebra, but I think the concept is important. And if it is clear to you, then we will, next class, we will sort of wrap this up, try to wrap it up as quickly as possible with the notion of elasticities. What do you think are the elasticities? And if you have the energy and the ability, then I would say what happens when these reactions are reversible. We derived the case for the Michaelis-Menten reversible kinetics. And now, with a very simple extension of the reversibility principles, you can talk of inhibition and reversibility simultaneously. So you see how the algebra becomes sort of complicated, but we will not get into too much of that. But you should have a feel and understanding of the fact of the 3 inhibition models derived from the most generalized model that I could think of. Okay, shall we stop here? This is clear, all of it?
Yes, sir.
Okay, thank you. So shall we stop recording?
Thank you, sir.
Thank you.